what I was telling you about is the whole purpose of this course, right? Last year also we had something like this that was based on the general theory, and in that we discussed how Einstein developed his ideas that led to the new theory of gravitation. What we want to do now is to understand how the atomic nucleus was discovered and different aspects of it. Firstly, I would like this to be an interactive session. Okay, so it'll be wonderful, because otherwise, you see, if it's a lecture, I think you'll find plenty of lectures online, right? And if it's only about listening, right, you could do it anywhere. The whole point of having this session is so that we can have a discussion. Okay, so feel free to unmute, interrupt, speak up, share your own ideas, your own understanding, to raise questions. And the most important thing is to be skeptic. Okay, if there's one thing you should learn from science education, it's not knowledge, it's not formulas or facts. Rather, it is the skill to ask questions, to question, and to question in a way that not just for the sake of questioning, but because you want to understand something, and also you doubt something. It's good to doubt. Okay, that's the whole point. If all the scientists that in fact you see in this poster here, all these are the major figures and that played a major role in our understanding of developing our understanding of the nucleus. If all of these or none of these, let's say, had the courage to ask questions, and in fact the habit, I think it's more of a habit to ask questions and to dive deeper. Rather, they were okay with just accepting what they were told, what they were taught, we would not have made as much progress as we have, right? So it's a common trait of all these thinkers is to ask questions, to raise, to be a skeptic. And of course, skeptic with rationality. Okay, so irrational skepticism is also not good. We see some of it these days. They think of the flat earth society, right? They call themselves skeptics, that they doubt everything. They doubt what NASA tells, and they don't think we landed on the moon and all such things, right? But that's a mindless skepticism. So it's important to be mindfully skeptic, to doubt, to not accept things that are told to you without doubting them, without seeking better evidence. Okay, and the evidence might be in the form of an experiment, it might be in the form of logic, right? We have broadly these two kinds of evidences. Right? So we have these two broad ways of verifying whether we are on the right track. Either conduct an experiment, see what the experiment results tell you, or at least what you're talking should be logically sensible. It should make sense logically, right? So that kind of skepticism is important. That's one of the key things that you should be learning in science education, is to ask questions, to raise doubts, and not accept what's being told, which unfortunately is not happening in most places, right? When you think of a classroom, doubts are not as much encouraged as they should be. So that's one aspect. So that means that you have to put in more effort, basically, to be to be someone who questions and who finds out. It should become a part of you, basically, and that's when you will start learning. And you will also be in a position to maybe come up with new ideas that nobody else has thought of, right? So that culture is necessary. Okay, and so that's one of the things here. Okay, so when we are discussing, feel free to unmute and speak up. And I believe in the words of Richard Feynman, who said that something like this: when you're studying something, don't care about the discipline or the reverence and all such things that come in the way of learning. Okay, so there's no such thing as an interruption or you're being disrespectful or nothing like that. Okay, so, and also there's no such thing as it should be systematic. I'm going to speak for a while for so many minutes and then you have 2 minutes to speak up, right? No such rules. So if you go about following rules, true learning will never happen, right? So there are no such rules that I should specify. Okay, in fact the rule is that don't follow any rules and just speak up. Okay, right. So firstly, when we are talking about this topic, right, the atomic nucleus, what comes to your mind? What is your expectation from the course? Because I'm building this course as we go about, so that from your feedback, from your expectations, I'll also be able to make it more aligned with what you expect. So maybe you can briefly share what your expectation is from this course. Okay. In fact, what you're pointing out mostly is to do with the understanding of the atom, right? So, yeah, right, okay. But you see, now we are going to talk about something much smaller, the nucleus, the heart of the atom, and we'll be diving deep into it, okay? So there'll be plenty of new stuff, and I'll try to, as we go about, include some very advanced ideas so that you get some understanding of what happens inside the nucleus. Right, okay. Sure, so what you said is you would want something new and not the same stuff that you've been learning. Sure, we'll have that. Others, you can share your expectations from this course. The nature of these forces, right? Strong and weak nuclear forces. Sure. We will be focusing on that as well. Yeah, you could also mention topics that you would like, because I have a set of topics in my mind. If there's something new and it's related, we can include that as well. But also feel free to share your overall expectation from the course. What would you like to learn overall? Or also the way of going about. Others? Yeah. Nuclear fission, yeah. Sure, that's on the list. Yes. Okay. Yeah. In fact, yeah. You see on the poster right behind Oppenheimer, right? That's nuclear fission happening. And yeah. Sure. Because it's very interesting, right? We hear so much about the bomb and how much destruction can produce on it, and we know that it uses nuclei, something to do with nucleus, but that gap in between is missing, I think, right, for most of you. That how do you go from a nucleus to the explosion that can cause mass destruction? Sure, we'll make that link. Yeah, sure. Yeah, that's another way of going about. Just be open to learning whatever comes your way. Yeah. Right. True. Sure. That, and it's linked to the carbon dating, right? How you find out how old something is. Yeah, we will be discussing that. That's it. Again, feel free to speak up at any point of time. Now, going about this, what we're going to discuss now. Firstly, let's begin from the beginning, right? So, where did all of this start? How did we begin to understand the nucleus? So, for this we have to go back to 1895. This was a time when the world was very different from what we know of today. For one, there were no airplanes, right? No telephones, and there was very little electricity, right? There were some companies like Edison's General Electric that was trying to set up electrical connections in major cities, but otherwise, yeah, yes. I'm trying to record, but I don't see an option on Google Meet to record. So, yeah. So the best I can do is I'm trying to capture the screen. I can record the screen and then I have to record my voice separately on my phone, and then I have to merge them together. So I'm trying that. It's happening now. But only drawback is your voices will not be heard because I'm hearing it in my ears. So anyway, let's see. At least something rather than nothing for the others who are missing. Okay. This is a group that's unique because this is not just limited to students of the current batch, but also the students from my previous batches and all students that I'm in touch with who are interested in physics. They're all being invited. So this is purely for the love of physics. Okay. Right. So what I was saying is, the times were very different back in 1895, and communication was through mail, and streets were lit by gas. These are things that we can't even imagine living with, right? After having all the technology that we have today, it almost seems impossible to go back to those times. So that is the in fact, I recently came across an interesting joke actually, that the question "Where are you?" right, is something that's relatively new, right? Back in those times, I don't think people ever had the necessity to ask "Where are you?" because the only way that you would communicate is through mail or some primitive telephone, and in either case you would know where the person is, right? Otherwise you wouldn't be able to send them the letter or make the call. So it is only the luxury of these times that we live in that we get to ask "Where are you?" right? Because the person could be anywhere and still we can contact them, right? Anyway, so this was also the time when there's a repetition here. And physics laboratories looked very different from what they look like today. There were very poor facilities, often also poor hygiene at times, and there would be a single professor who's in charge of the lab, and many times he sleeps in the lab, and 99% of the times it is he and not she, right? That's another thing that was different. This I just mentioned 1895, right? Yeah, so it's all around 1895. So right, and it would be a male professor 99% of the times. In fact, I think 99.99% of the times, and very, very, very rare that there would be a lady who's doing the experiments and staying in the lab. And the laboratories were ranked based on the power of the battery it owned, right? That was the big, a big thing. You have a better battery, that's a better lab. You can have lights lasting for longer. You can have power for longer, right? Before it runs out. And these are things that we don't even think today. Electricity is taken for granted, and there's no battery. You have continuous supply of electricity, and we have more advanced demands today. But those were the only times those were times that were different. So there were no mains at all, so that you could draw electricity from, right? So there was no electrical connections that we see of today. And the other thing that was different is the existence of atoms was a big question mark. Okay, we weren't sure if atoms are real. There were some people, very few people, that like Boltzmann and Gibbs, who were working on developing a theory of gases, assuming that gases are made up of atoms or at least molecules. But not many people were paying attention to it. They, in fact, they often thought that atoms are a thing of fiction, right? And the reason for this lack of belief in atoms was not that you cannot find atoms, you cannot see atoms, right? The whole point is that the existence of atoms was not, also it was not that atoms is a very complicated idea, right? It's very hard, only the smartest people can understand what atoms are. That was also not the case, right? So rather the problem was the absence of evidence. If you do not have evidence of existence of atoms, and it's not established that atoms are real, then how do you go about saying that let's assume atoms are real and let's go ahead, right? How do you make that start? How do you know you're on the right track then, right? So that was the big question during those times. It was only in 1905, around that time, Einstein was one of the contributors to this, establishing that atoms are real, at least molecules are real. And until then, the theory of atoms was rejected, right, by most of the physicists. Or at best, it was treated as a tool, a useful tool. Some even compared it with, I think it was Lord Kelvin, who compared it with algebra, right? Algebraic symbols like plus, minus, into, divided by, right? All of these are useful things, doesn't mean that they're real. You can't go about finding the plus sign that you write when you're adding two things. But still it's useful for you to calculate things. So similarly, some people thought that atoms are useful because they're giving us some results, but that doesn't mean they're real. Right? So that was the kind. And you see, it's not too far ago. Right? 1895 is just about 120 years ago. And the times were such that people didn't, most of the leading physicists of the time didn't believe in atoms. And so, so this is what I told you. Atoms were compared with symbols of algebra, right? And so atoms were not, the lack of evidence of atoms, one obvious way in which the evidence was lacking was in terms of seeing, right? You cannot see atoms. You can only see it through your mind's eye. You can only imagine atoms in your mind, but you cannot see them. But do you think that has changed today? Right? In fact, let's quickly think about it. Have we seen atoms today, do you think? Or what's changed from those times to now? We haven't. Yeah, nobody has seen atoms even today. But we very confidently speak about atoms being real. There's no doubt about it. If you find some person saying, I don't think atoms are real, you would think twice about talking to that person the next time, right? Because it's such an obvious fact today that atoms are real. But so what has changed exactly from 1895 to now 2023? How do you think we have all of a sudden, not all of a sudden, gradually been convinced that atoms are real, even though in terms of seeing atoms nothing has changed? We still do not see atoms. Back then in 1895 also people couldn't see atoms. What made them accept? What made them accept? What could have made them accept? Is it just a change of mind? Because if it's just a change of mind, it's possible to go back then. After a few years, maybe people will again start saying, no, I don't think atoms are real. But that's not going to happen, right? Yeah. Right. Okay, the simple idea is, I can give you one example of several of hundreds of examples, is heat. So when you say that something is hot and you touch and you feel that it is hot, and then you ask, where is this heat coming from? Meaning, what's the origin of this heat? What's happening down there, right? At the very deepest, at the smallest scales. And then if we imagine that there are atoms that make that object and those atoms are jiggling at a particular speed, you can account for all the heat that's coming out. Okay, so you can sort of reverse engineer. You can say that the heat is coming there because the atoms are vibrating, and it all fits perfectly. It gives you the perfect results, and this is just one aspect of it. Okay, so like this, think of the hardness of the substance, hardness and softness, the texture, the color, including the color. All of this can be explained using atoms, right? So, right. So this way there are indirect evidences. That's the key thing here. Okay, you might not be able to see atoms, but there are evidences, and the evidence, like it's mentioned here, is better than evidence for miracles and for flying saucers, not slaying saucers. Sorry, it's flying saucers. So we have better evidence than I think recently you came across in the news. They have found these bodies of aliens, right, with big heads and big eyes, 3 fingers, right, and that's the kind of evidence we're talking about, right? But of course, that still has not been established that it's an alien origin, which is in fact very unlikely. Did anyone come across such a thing? And also think of, see, this is where also logic comes in. Okay, you have evidence. Are you going to accept it? Okay, and based on what are you going to accept it? So in fact, thinking of it broadly, the moment there's something like this that comes up, there are 2 things you can do. Either you can accept it blindly, or you can reject it blindly. Correct? I think both are equally bad. Okay. So while you might say accepting blindly is more, worse thing than rejecting blindly, I think both are equally bad because you're being equally lazy both the times, right? You're just rejecting something without even giving it a second thought, which is, I think, as bad as accepting something without a second thought. So no, let's not criticize each other now. Okay, so yeah, right. So so the idea is that once evidence is presented to you, how do you go about analyzing it and making sense of it and saying that it's unlikely to be true, or why do you say it's unlikely to be true, and so on. And in the case of this alien thing, that the fact that it's a humanoid figure, right, with hands and legs and head and so on, it's developed on some other world, feels very unlikely, right? Because most life form on Earth doesn't look like humans, and which developed along with us on this Earth under these conditions. And then you say that some other life form on some other planet under very different conditions developed a life form that looks very much like humans, right? That's extremely unlikely. Okay, I'm not saying it's impossible, but the likelihood is really, really low, right? So based on that itself, your skepticism should begin, and you should start saying that I don't think this could be true. And if it is true, it's a very, 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 very rare happening that has happened, right? And still you don't reject it, right? That's the key. You don't just reject it based on that. Rather, you say, I'm open to the possibility that maybe it's actually alien life. But let's investigate further, right? So let's do some DNA testing and something like that and try to figure out. Let's check the composition, the elements that it's made up of, and so on, right? So that's one of the things you should keep in mind. Do not reject something blindly and think that that's more superior than accepting something blindly. Okay, right. So here with the existence of atoms, right? It just turns out that it's not like we have enough evidence to that will ever be enough to convince ourselves. The idea is that we have better evidence. Okay, compared to 1895, today we have better evidence for existence of atoms, and that evidence is better than what we have for miracles and flying saucers. So going back to those times, what exactly happened, right? So let's look at the series of events that led to the discovery of the nucleus ultimately, okay, because there's a long chain of events that happened beginning in 1895, and that was the year around that time, between 1895 and 1897. There were four major discoveries that occurred. One was the discovery of X-rays, and by Röntgen and a German physicist. It was a completely accidental discovery. The discovery of the electron by J.J. Thomson, the first atomic particle to be discovered, subatomic particle. And there's something called Zeeman effect, which initially supported the theory of electrons and later, in fact, helped very much to understand how atoms behave. And radioactivity, which is one of the things that we will be focusing on in today's session. Okay, so which was propelled by the likes of Henri Becquerel and Marie Curie and Pierre Curie, and all these people. And it started with the first experiments that were being done during those times that led to these series of discoveries was to do with the cathode ray tube, what you see here. Right? This is basically a glass tube from which air has been sucked out. Okay? It's a vacuum. Air has been pumped out, and it has been sealed so that we assume there to be, in the most ideal case, we assume there to be nothing inside this tube, not even air. It's completely empty. Right? That's what we call vacuum. And this is known as a cathode ray tube, basically. Okay. So the idea is that when you pump air out from this, right, and you create a partial vacuum, because back then in 1895, back then in 1895, creating close to perfect vacuum was very hard. In fact, even today, in labs, what we do, we try to create vacuums, but those are no, we cannot claim that they're 100% vacuum. Okay, you can reach 99% or 99.99% vacuum, but 100% vacuum is very, very hard, almost impossible. Because to make sure that there is 100% vacuum, you should make sure that there's not a single atom of air inside that, that region. And back in 1895, we had good methods to create vacuum, but not perfect vacuum. So we had partial vacuum. And what you do is you have two electrodes on the two ends, which are connected to maybe a generator, right? Generator of electricity. And the moment you switch on the generator, what you will see is a very thin, strange arc, a lightning spark-like line that joins the two ends of the electrodes, the cathode and the anode. Right? And this was something very strange. I can show you now. So this is what an arc looks like. Okay, this is a more modern picture. I hope you can see. It's a very faint, and of course this is a sort of more compressed cathode ray tube with anode and cathode pretty close to each other. But you see this kind of an arc, this glow, this purple glow that you see. And naturally, there's something like this fascinated people back then, because there was no explanation for these. In today's times, it's easy to explain. There are atoms. Since it's a partial vacuum, there are some atoms left in that chamber, and those atoms are getting excited and they're getting ionized and so on. And you can explain that these charged particles are flowing across. But in those times, there was even the electron was not discovered yet. The electrons were not discovered yet, and therefore there was it was a thing of fascination, that this is something you could see, but you could not explain. Right? I think what intrigues anyone a lot is the when you can see something and still not be able to explain it. Right? That's when I think you simply cannot hold yourself back, and you want to find out what that is. And so this was a fascinating thing. And those came to be known as cathode rays. But even before that, there was a development that what happens with better technology is what happens with as technology develops is that your experiments get better. So with time, the vacuum that was being created became better over time. And in fact, here is one more situation that happens when you decrease the pressure further. Okay, so if you can get better vacuum, it turns out that the whole gas inside that's left over starts glowing, and it looks something like this, somewhat similar to a neon sign. And this was even more. Sorry? No, it's not like needing vacuum. The idea is that that air does not conduct, right? And so if you simply have two electrodes lying around at some voltage, you don't see any electricity passing in between, right? But if you were to rarefy the air, reduce the air, then you start seeing these effects, right? And of course, yeah, that's the whole point, right? And while trying to pass through the gas, it hits the gas particles and causes them to excite, and they start glowing, right? So again, all of this I'm again telling from the modern perspective. So what I'll try to do is I'll try to keep it as much as possible. Let's stay in the mindset of those people of 1895. All you see is that you have this tube from which gas has been partially pumped out, and then you connect it to a battery or a generator, and the gas starts glowing like a neon sign, right? And so people want to find out what's causing this, because at that time there were no theories for this. Newton's mechanics was a major success, but how can you use that to explain glowing gases? How do you explain thermodynamics? Something to do with how heat flows from one place to another. That's something to do with this exactly. Electromagnetism, the theory given by Maxwell, was successful, but again, how do you apply it here? Because you see, we needed the understanding of atoms and nuclei to understand this, and that didn't exist at that time. So you see, you're in a time in 1895. If you were to be in those times, you'd be seeing things to which explanations to which would lie in the future, right? Theories were not yet developed that would eventually be able to explain those ideas, and that actually is the essence of science lies in there, right? Just think of how many things today that we do not know, the answers to them will lie in the future. And if someone were to come from the future and be able to explain us all those, answers to our questions, we would not even be in a mindset to be able to understand those answers. Okay? Because we don't even know what questions to ask. And similarly, you can imagine in 1895, if we went back in those times and started explaining to those poor guys who were fascinated and unable to understand what's happening, that there's such a thing as atoms and all of this, right? They would just think you're crazy. Right? Because they're not even in the mindset to think in those terms. So that's how science progresses, right? You go from knowing nothing to knowing something, and then to the extent that you know so much that you cannot go back. And even if you went back, you cannot go back personally. Meaning, once you have learned something, you can't unlearn it. It's there in your mind now, right? And also in the way that if you were to go back and explain to your own old self, your old self would not, himself or herself would not be able to understand what you're trying to explain, because the vocabulary would be very different. There would be a lot of assumptions, and there would simply be too much to explain, right? And it would take a very long time for you to finally get a grasp of it. And so that was one observation. The other observation that was even more interesting is that you decrease the pressure even more, you pump more air out of the tube. The tube goes dark, okay? But on the back side of the tube, where the cathode rays were assumed to be, I hope nobody's waiting. If anyone is waiting to join, just let me know. Okay, yeah. So on the back side of the what is known as the anode, the glass would start glowing, and it would start glowing green, right? An eerie green color. And this is known as fluorescence. Okay, something that starts glowing when caused to excite with some radiation. And this was very interesting because the radiation that is causing that glow itself is invisible, right? But it's causing the glass to glow visibly, and that is something strange. And you switch off the battery, the generator, this glow goes away. Okay, you switch it on again and the glow comes back. And as you can see, inside the tube it's very dark. There's nothing inside the tube. You can't see the radiation that is causing this this glow, but what you can see is the glow itself, and we are unable to explain what's causing that. So people said that there's something called cathode rays. That's why it's called a cathode ray tube. The cathode rays that are starting from one end of the tube going all the way to the other end, and on missing the other end, some of those rays miss reaching the other end. Those are the ones that go hit the glass, and they are causing this glass to glow in such a way. And so people had at least a name now, right? Cathode rays. They wanted to find out what these cathode rays are, these mysterious invisible rays that are passing through this tube and causing this excitation. And they started investigating, and this was one of the experiments that they did. They placed some obstacle in the middle of that, in the path of that rays where the cathode rays had to pass through, and they found a shadow on the glass on the other end. You didn't see that green glow in exactly that shadow region. And what does that indicate? How is this useful? Or what are the conclusions that you can draw from this? Exactly, right? Yeah. We often say that the evidence that light travels in straight line is in the fact that it casts sharp shadows, right? If you're getting sharp shadows, that means the light is traveling in straight line. Same idea here, that the fact that you're getting the sharp shadows indicates that whatever that's traveling, which is invisible, at least should be traveling in straight lines. Okay, and this is, I think, again something very interesting, right? You have first of all, you identify that there's something traveling, even though you cannot see it; it's invisible. And then you don't just give up and say that, okay, there's something invisible, okay, so let's move on to the next thing. No, you're interested in the invisible, right? You cannot see it, but you can still investigate it. And then you go about doing things like this, right? Where you put an obstacle in the path of it and see what happens, right? And this is often, the kind of playing around that is done by scientists, right? They're almost like children, right? Trying different things and not giving up, right? Until you figured out something. And so this was one of the modifications they did, and they found that you have this dark, the shadow, right? And these are known as cathode rays. These are traveling straight. And as for the nature of the cathode rays, what exactly they are, across Europe, where all the development was happening, physicists were divided. Some thought that these are particles. Some others said that no, they're waves, because only waves can do such things. Some others said no, it's particles traveling in a straight line, right? So they were divided. That's when Thomson comes in, right? J.J. Thomson, who is considered the person who discovered the electron for the first time. He comes about, and he is also doing experiments with cathode rays. And his main purpose is to find out what these rays are actually. And so you see, he had no idea that he is going to discover something new, right? All he is trying to do is just investigate what it is, what are cathode rays. And in that process, he basically modified the cathode ray tube slightly. Okay, what he did was, he passed these cathode rays through, instead of placing an obstacle in the path of the rays that others did, he instead brought a magnet nearby. Okay, so what happens when you bring a magnet near these rays is that the rays are going to bend. The cathode rays are going to bend. The path is going to change. And that's something interesting, right? So you can play around with the cathode rays now, right? You can move the magnet close and the ray bends away. You move it away and then it continues to go in a straight line. So what we can say is that this magnetic field of the magnet is influencing the cathode rays. It's possible to manipulate these rays using magnets. But what Thomson also realized is that you can also apply an electric field. Okay. Now, those of you who are not familiar of electric field, think of a charged comb, right? Run your comb through your hair. I think all of you have done this experiment. Run a comb through your hair and bring it near bits of paper. The bits of paper cling to it, right? So we say that when you are rubbing your comb through your hair, you're charging the comb. You create the comb then has an electric field. Okay, just like a magnet has a magnetic field, a charged comb has electric field. So when you pass both an electric and magnetic field both together on the cathode ray, and then you see what happens, right? So the basic idea is that while the electric field causes a deflection one way, the magnetic field causes a deflection the other way. Okay, so you have these two opposite effects. And what Thomson did, the clever thing, is that he put both magnetic as well as the electric field simultaneously. And then he set the strength of the fields in such a way that there was no deflection. And from that he could calculate, right? Not just guess, but he could actually calculate from these observations what the charge and mass of those particles should be. If cathode rays are made of particles, what is their charge, electric charge, and what is their mass, how heavy they are. And that is marked as the discovery of the electron. Okay, so Thomson, through these clever experiments, which of course I'm not going in depth here, I'm not going into the mathematics of it, because I have one thing is that I'll keep the mathematics to a minimum, and also that this is not the main focus of our discussion, right? This is something that we are going to pass by, so I'm going to go through this quickly, because this was the first subatomic particle discovered, electrons, right? And this is basically half the atom. Inside the atoms we have nucleus, and along with that we have the electrons, right? That's what makes an atom. Anyway, so I think you can look it up. What are the exact calculations that it did? It's a very simple calculation. You just need basic algebra to be able to do the calculations. And you can yourself figure out what the charge to mass ratio should be. Okay, and he basically figured out that these cathode rays are actually beams of electrons, right? Then you could start imagining that these invisible rays that people were so fascinated about are actually beams of electrons, particles called electrons. And the electrons have a negative charge, and they get deflected when you bring a magnet nearby, or you apply a magnetic or electric field near it. And what he also discovered is that, now of course you don't do this and then you stop, right? If you have half the curiosity of a scientist who's discovered something, you're going to go ahead and you're going to proceed, and you're going to try to find out, try to change the conditions and repeat the experiment, right? So he instead pumped the air. He used other gases other than air. He used hydrogen, he used oxygen, and he repeated the same experiments. And what he found was, every time he found that the cathode rays are the same, no matter what material you have, what gas you have inside the tube, right? And this led to the conclusion that the cathode rays are not something that change from situation to situation, but rather they're universal. The electron that is discovered is universal. It's present in all matter. It's not just in this gas or that gas. It's there everywhere, right? So that was the genius of Thomson, right? The conclusion that electrons are universal. They're found in all matter. And again, this was a time when atoms were not real, okay? Atoms were still debated, but the evidence for electrons was unrefutable. It was clear that electrons exist. But how they exist, what they actually are, what is their size, and all of that is yet to be found. But at least you cannot deny that electrons exist. And that is one of the things with how physics grows, okay, how science grows. We often hear that new discoveries replace old ones, right? Or prove that the old theories are wrong, right? But that's wrong to say that. what happens is that new theories come and they just expand the old theories. They make they explain everything that the old theories were explaining plus the new stuff, right? But what a new theory cannot do is that show that the old theory was completely wrong, okay? Because if it was completely wrong, then what about all the experiments that were working according to that theory, the old one? So you cannot undo all those experiments, right? You can only expand and say that now new experiments are also being covered under this better, newer version of the theory. Okay. So similarly, once the electrons were discovered, no, but pure water doesn't exactly conduct, right? Only if you put some salts in it, right? Sorry. Okay. So basically electrolysis happens, what you have studied in chemistry, right? Something similar happens, but what happens is that the atoms will tear apart and the ions will move one way, the electrons will move the other way. But what you will not see is a glow, okay? The glow that we see with the gases, it doesn't even happen with air. That's why we want very rarefied air. You can pump air out of a tube and reduce the pressure of the air inside, but you can't do the same thing with liquids, right? With liquids, either you have liquid or you don't have the liquid, right? So there's no low pressure liquid. So meaning you can reduce the pressure of a liquid, but the number of atoms will remain the same, right? The density remains the same, right? So such experiments were very so with gases you have a lot of flexibility, right? You can reduce the pressure, you can reduce the number of atoms, you can play around with the density, you can make it close to vacuum, almost vacuum, right? So all of that. And he didn't just stop there, and he in fact made a prediction, right? That's one of the things about new theories, that if you want to establish a theory, you have to make predictions that can be tested. If you cannot come up with predictions that can be tested, your theory is of no good use, meaning how do you even know that the theory is correct? How do you verify? In fact, we use the term falsifiable, okay? So the theory has to be falsifiable, meaning you should be able to say that if you do such and such an experiment and you get this result, you can prove my theory wrong, okay? And then of course make the claim, the bold claim that no, you're not going to be able to do that, right? Because I have run so many experiments. Even you run your experiments, you should not be able to come up with different results, wrong results, right? Results that don't match with my predictions. So the ability of a theory to predict new things, new phenomena, to make new predictions is where its strength lies. You cannot prove a theory. And that's one of the things in science. It's impossible to prove any theory. To prove means to say that I have run all possible experiments and in none of the experiments my theory disagrees with the results from experiments. That's a claim that nobody can make, right? Because how many experiments have you run? Maybe 1,000 experiments, maybe 10,000 experiments, but what do you know that someone tomorrow might come up with one more new experiment which seems to not agree with what all the experiments that you've done so far, and your theory doesn't seem to match there, right? So you can only verify, you can make predictions and you can verify the theory, but you cannot prove it, right? And one of the predictions that he came up with here was the mass of the electron. And of course with his crude methods he could only say that it's 1,000 times smaller than the lightest element we know, hydrogen, at that time, right? Even today hydrogen is the lightest element. The electron is 1,000 times smaller, and today we know it's exactly 1,836.15 times smaller, so we know with great precision. And then came the discovery of X-rays, which is the reason why I took up cathode rays here, because there's a link here, right? There was this obsession with understanding cathode ray tubes, how cathode ray tubes and what cathode rays are. And one of the people who was obsessed with this was Röntgen. Wilhelm Röntgen was a German physicist, a professor of physics, and he was very curious about the cathode rays, and in trying to figure out what cathode rays are, he was performing an experiment. There's this particular day on November 8th in 1895. In the evening, he is in his lab and he is doing these experiments and with cathode rays, and he has put a black cardboard on top of the on top of his cathode ray tube so that no cathode rays can come out. And to his surprise, he sees that there is a screen at some distance from the cathode ray tube which starts glowing every time he switches on the cathode ray tube. And even though he has put a black cardboard on top of it, on top of the cathode ray tube, and he is completely mesmerized. There's something that's traveling from here to there to the screen which is invisible, and it cannot be cathode rays because cathode rays, remember, they cannot travel through air, and there's air in the room, and the cathode rays are not traveling through all that air and reaching the screen. There should be some other radiation that is invisible, and it's not cathode rays. You see, that's the interesting thing. He is trying to understand invisible rays called cathode rays and stumbles across another type of invisible rays, right, which were not cathode rays. And as if the fascination with cathode rays was not enough, now there's a new thing here, right? There's a new kind of radiation which he chose to call X-rays. Anyone can guess why he called them X-rays? What could be the reason? Right? Because he didn't know what these rays are. They were unknown, right? And usually in mathematics also, unknown we usually call X, right? X, Y, Z, X particularly, right? Very famous variable. And today, even though we know a lot about X-rays, we still call them X-rays because the name has stuck, right? And so I in fact have a clip of it for you, which I will try to play it from here. Yes, audio? No? Okay. It's only me who's hearing it. Anyway, so this is a clip from a series on Einstein. This is Röntgen. That's the cathode ray tube that he's using. But then share screen with audio. Just share screen. Anyway, there's not much dialogue here. Okay? Yeah. Anyway, there's not much dialogue. Okay? So just observe that he's working alone, and you see he puts a black cloth on top of it. Right? Did you see that? He covers the cathode ray tube, switches it on. Actually, he covers it with a black cardboard so that no rays can come out. And then he sees on one end of his room there's something glowing. There's a screen that starts glowing. And so naturally you switch it off and the glow goes. Switch it on, the glow comes back. So there's something mysterious that's traveling from his apparatus all the way to the end of the room to that screen, causing it to glow. And then he gets obsessed with it to the extent that he's working day and night, and his wife is worried what's wrong with him. And then in trying to explain it to her, he takes the first X-ray, right? And this is in fact the first X-ray ever taken, X-ray scan. And his wife exclaimed that I have seen my death, right? So those are the famous words. And that was the discovery of X-rays, and which of course Röntgen thought that it's going to make him famous, and it's but he was a very isolated person, so he would rather not be in limelight. He would rather shut himself in the lab and investigate it further. So the next several months he shut himself off, and he started working to try to understand these X-rays better. Okay, so that was it was a completely accidental discovery, right? So that's what's interesting, is that there was no he didn't sit down on that particular evening to make a discovery or or he didn't have the faintest idea that he was going to come up with anything new. All he wanted to do was do some experiments with cathode rays to find out what they are, and in that process he discovers a new type of radiation called X-rays. So something must have hit the screen, right? That causes it to glow, and this was a very unexpected phenomenon. Right? And then he tries different setups. Right? He tries to move the distance, change the distance, use different material for the screen, a photosensitive screen. Right? This is a screen basically that glows when some radiation falls on it. Okay. The basic mechanism in a modern language is that the atoms of that screen absorb radiation of a particular frequency and they give out of a different frequency. So you can see visible light. Even though X-rays are not visible, the light that the atoms emit is visible. It's greenish, some depending on what material you use. And that's called fluorescence, that process called fluorescence. Something similar that happened with glass, remember, with cathode ray tube? The behind part of the glass tube would glow green, right? So, and that was caused by cathode rays. Now we have another glowing here, which is not caused by cathode rays, right? So it's this glowing that is giving away, that is revealing that there's something invisible, that is causing something else to be visible, right? And then you start doing experiments and you find out that it is not cathode rays. It should be some other radiation which you call X-rays. And these were so remarkable that, remember, while cathode rays were casting a shadow, right? When you place that cross or whatever in the center or some obstacle in the center, it would cast sharp shadows. X-rays don't seem to be casting shadows, right? They seem to be just passing straight through any material. Most objects that are opaque are actually transparent to X-rays. And that is the reason that you can take a scan of your bones, right? You're basically having X-rays pass right through your flesh and skin as if it's transparent, and the bones being slightly more denser, they're casting a slightly sharper shadow. And what you see in an X-ray scan is actually the shadow, right, of your bones. And they're actually passing through the bones also. That's how they reveal fractures, right? If there's any crack in the center of the bone, you can see that as well because X-rays are passing right through that as well. So this was something remarkable. So that established that these are not cathode rays, because cathode rays don't pass through everything, and also they don't pass through air. And here we have a situation where the X-rays are doing both the things, right? They're passing through opaque objects. And the moment the publication was made by Röntgen, it made newspaper headlines, especially because it was very catchy because of that photograph as well. This was the photograph, right, of his wife. This is the actual photograph, the first X-ray scan ever taken by Röntgen of his wife, and you see the wedding ring also there, right, on the ring finger. So this was the very first X-ray scan done, and this became a headline, right, in the newspapers, that now we are able to see through the bones. And some people even started being afraid of privacy, right? Can X-rays then see through clothes, and right, if they can see through bones, right? All such mystery was surrounding these new radiation. And and ultimately there was now the moment Röntgen announces, right, makes this announcement, what do the other scientists do? Like I said, there was an obsession during that time with cathode ray tubes, and almost every notable physicist had a cathode ray tube with them. So what they did was, the moment they found this out, they rushed to their laboratories, switched on the cathode ray tube and repeated this experiment, and they got the results. They again could see the same effect that Röntgen had seen. And somehow all of them had missed it, right? And Röntgen was the one who noticed it for the first time and investigated it. And that's in fact something that happens throughout science discoveries. It's not like one person comes up with a discovery and everyone says, gives a thumbs up and says, okay, we agree with your results, right? In fact, it's the exact opposite. The moment there's an announcement, especially a big announcement, all the scientists are going to go back, they're going to repeat the experiment in the hope of disproving that claim, right? And they try all possible ways of showing that this is not the case. And when they cannot show it, that's when they accept it. That's, if you cannot disprove something, you have to accept it. And that is how science progresses, which is very different from how any other idea progresses, right? Any other political thought or religious thought you just have these ideas and then you just have to accept them, right? That's the exact opposite in science. You have to reject everything, right? And then you have to accept only things that you cannot disprove. And that is why we have this entire set of ideas, this collection of facts and things, that ideas that work, because anything that does not work has been filtered out, and only what works remains. And that is when comes this remarkable person called Henri Becquerel. He was a French physicist who actually was a descendant of at least 4 generations of Becquerels. Okay, all those were notable scientists of their times, and he was the great-grandson and the grandson and the son of notable physicists. Right? All of them were Becquerels throughout the 19th century. And his father was a curator of a museum, the National Museum of France. It's the Museum of Natural History in France. Right? He was the president of it. And once his father passed away, he took up the position. So in his father's position in that museum, there were all sorts of strange things related to science. And one of them was uranium. Okay, uranium salts were passed on from generation to generation, in the Becquerel family. And Henri Becquerel particularly, he had these uranium samples and he got curious. Right? After attending a lecture on X-rays, which were still new at that time, around 1896, he thought that why not I try to find out if X-rays are coming out from uranium as well, because uranium was known to fluoresce. It has the phenomenon of fluorescence, which means you shine light on it, it starts glowing, right? And in that glow, Becquerel thought maybe there are X-rays also coming out, and there were enough techniques to find out if it is indeed X-rays or even cathode rays. But he knew that it's not cathode rays. He wanted to know if it's X-rays that are going to come out from uranium. And uranium is extremely rare, right? It's a very it's found in very small percentages in the Earth's crust, and it's a very rare material. And today, it's indispensable if you want to create a nuclear bomb or a nuclear reactor, right? You need uranium. But at those times, of course, nobody was thinking of a bomb or a reactor. Uranium was just lying there, right? It was, in fact, uranium was used in glass utensils to make them glow green. And today, none of us would drink anything from such a glass, right? But back then, people didn't know, and they used to use uranium as a decorative material that causes glass to glow, crockery basically to glow, right? And so Becquerel was curious to find out if it is X-rays that are coming out from uranium, and he found out that it does not, right? So the fluorescence of uranium is not nothing to do with X-rays. And then he actually did a few experiments. He took the uranium salts and he exposed them to sunlight. So the basic idea, the way uranium works, the way uranium glows, is that you have to subject it to light, some radiation, some sunlight, let's say. Okay, so you keep it in sunlight for a while, and then what the uranium does is it absorbs all that sunlight and then starts giving out some greenish color, right? It starts glowing. And this is how fluorescence works. Fluorescence is this phenomenon where you have some radiation falling on some material, and that material absorbs that radiation and gives out its own radiation, right? And then what he did was the radiation that is emitted due to this fluorescence produces a shadow on the photographic plates. Now you know how photographic plates work, right? Of course, today we don't use photographic plates because we have digital cameras, right? Back then, there used to be these photosensitive plates on which there is a chemical that is spread out, which is very sensitive to light. If light falls on it, that part starts developing, right? And you have a spot, a dark spot. And that's a negative basically, which if you develop, you will get the positive out of it, right? So every time light hits a material, that substance, the photographic plate, that spot becomes dark. I hope you know what negative means, right? Negative of an image. You develop the negative and make it positive. I hope you know this, right? How this works. I think just a couple of decades ago, there used to be this, even today we have reels, right? We have these camera reels that capture photographs the way digital cameras don't, right? The depth that they capture with. Anyway, so this was the idea. So what he did was he would wrap these photographic plates with some thick black sheet so that they don't get exposed to sunlight. And then he used to place a layer of uranium salts on it and then keep it in sunlight. So what would happen? The plates would start developing not because of sunlight, because they're blocked from the sunlight, but because this uranium there's a layer of uranium on top of it, they would start developing because there's radiation coming out from uranium which can pass through that black, covering, and it can cause the plates to develop, right? And you see dark spots on it. And it is by analyzing those spots on the photographic plates that Becquerel would try to investigate, are these actually X-rays? And on one particular day, what happened is that, of course, he tried to make sure that there was it was not chemical reaction, so he placed some salts. He placed a glass sheet between the salts and the photographic plate, basically trying to make sure that it is watertight, right? And then he found out that on one particular, I would say fateful day, series of days, actually 2 to 3 days over a weekend, there was no sunlight, right? It was cloudy, because of which Becquerel tried to get some imprints on his photographic plates, but it was not enough sunlight. So what he did was he put it in a drawer of his table, closed the drawer, and went back out. And it remained cloudy for the next 2 days. And since the sun was not coming out, he thought, why not I develop whatever I have, whatever faint, shadows that the uranium salts would have produced because of that faint daylight, which is not exactly sharp sunlight. He would do something rather than do nothing, right? Since it was continuing to be cloudy. And then he took out these plates and developed them, and to his surprise, he sees sharp shadows, right? Not faint shadows. You'd expect faint shadows because its sunlight is not there basically in the form of bright sunlight. You just have daylight, and that daylight can only cause the uranium salts to absorb a very little bit amount of energy, and they'll start glowing with a very faint energy. So you'd expect to see very faint markings. In fact, these are the exact. This is the actual picture of that very first, faint sharp shadows that he got. And these were the uranium salts that he had placed on top of the photographic plates, which was developed later, right? And of course, these to someone who is not aware of what's happening here, for them these are just smudges. It's a smudged paper that has to be crumbled and thrown away. But Becquerel knew the value of this. These are shadows of uranium salts which are produced not because uranium has been exposed to sunlight, but without exposure to sunlight, which means uranium is producing radiation which has nothing to do with the sunlight, which has nothing to do with causing it to excite and produce this radiation. And here was a discovery of yet another type of radiation, right? An unknown radiation which came to be known as Becquerel rays. So you see the chain of thought here, right? The chain of series of events, the wonderful series of events, right? Cathode rays were the initial obsession of physicists, right? And they were trying to understand cathode rays. Röntgen, in trying to understand these cathode rays, accidentally discovered X-rays. Also, J.J. Thomson, in trying to understand cathode rays, accidentally discovered electrons. Okay, and here comes Becquerel, who, trying to expect X-rays to be coming out from the uranium salts, discovers yet another type of radiation, right, which came to be known as Becquerel rays. So you can imagine in this span of 3 to 4 years, according to our current understanding, Becquerel rays are basically alpha particles. Okay, so alpha, beta, gamma, in fact all three. Okay, but mainly alpha. Okay, so yeah. Yes. Sorry? Oh, this is radioactivity basically. Okay. It's used for curing cancer, for example, right? So you use radioactive materials to cure cancer. You use it in nuclear power plants. You use it in that's what causes a lot of destruction in nuclear bombs as well, right? The radiation, death due to radiation, right? It's that radiation that we're talking about here, right? Yeah. But in the context of those times, 1895, this was completely unknown. You see, it's like there are a series of unknowns. You don't know what cathode rays are, you don't know what X-rays are, and now you have Becquerel rays, and all of it happening around 1895, right? And unfortunately, due to the excessive, obsession with X-rays, a lot of people didn't even think of investigating Becquerel rays. They just forgot it. They just said, "Oh, maybe Becquerel rays are just another type of X-rays," and then they were busy doing their own studies of X-rays. And Becquerel was left to himself. He was the only person trying to do more experiments with these, and at some point he also stopped, right? But that was the state at that time. So Becquerel rays were forgotten for a while, right? And that is when Marie Curie comes in, right? Maybe you've heard a lot about her, right? And her story is simply remarkable. Being a woman, first of all, in those times, and a scientist who is a woman and who is trying to do this thing that, like I said, 99.99% is a male profession, right? And she comes in and tries to understand radioactivity, right? And succeeds. So the story goes like in 1897, after she married her husband, Pierre Curie, right? That's where the name Curie came from, right? This family name. Before that, her name was Sklodowska, okay? Marie Sklodowska. That was her original name. She was from Poland, and after her marriage with Pierre Curie, who was also a physicist, she asked her husband, right, I want to write a doctoral thesis to do her PhD basically, and suggest me a topic. And Pierre Curie suggested, why not you study Becquerel rays, which is something that's not investigated much. She basically wanted a topic that not many people were working on, so that she could get some new results. And she started working on Becquerel rays, therefore, right? And that was part of her doctoral thesis. And so she tried to do a number of experiments trying to understand what exactly Becquerel rays are. These are rays coming out from uranium, right? And she found out that the amount of radiation, the intensity of radiation, depended upon how much uranium was there in that particular compound. It was also not like uranium was there, like pure uranium, right? It was basically ores that you would get from the earth, which contained some percentage of it was uranium. The rest of it was other atoms, right? Other elements. But there was some uranium. So depending on the concentration of uranium, how much uranium there is in that sample, in that compound that you have, the intensity of radiation would be high. So there was a one-to-one link between uranium and the radiation that's coming out. So it's purely to do with uranium. So firstly, you make sure that it's not something else that's contributing to it, but only uranium. Right? And also it didn't matter what form the uranium was in. Right? Uranium was in the form of compounds. Was it an oxide? Was it a salt? Or was it metal? Right? So it didn't matter. As long as there was uranium, this radiation was coming out. And it was constantly coming out. Okay, it's not like uranium, again, like Becquerel discovered, you don't shine light on uranium and then uranium starts glowing. Rather, uranium is always glowing, right? Whether you put it in a dark room, you put it anywhere, if you bury it underground, it's always giving out this radiation, right? And those were the Becquerel rays, right? So those are the first investigations she did. And then she confirmed Becquerel's discovery that it has to do with atomic property, right? That was something that, like I said, atoms were still not real, right, at that time. But here was an evidence that if it is always uranium that is causing this radiation to come out, then it has to be the atoms of uranium, right? And also being a chemist, atoms, by the way, were more accepted in the chemistry, circles than in the physics circles at that time. Okay, because atoms help the chemist to explain chemical reactions, how you can take certain proportions of reactants and then get those exact same proportions of products. You could explain that very well if you assumed atoms to be real, right? So she was partly chemist and partly physicist, right? So at that time there's not a very sharp line between chemistry and physics. And so she was more inclined towards assuming that atoms exist, and she in fact suggested that maybe it's an atomic property that atoms are behaving a certain way and they are producing these radiations. And then she didn't stop there, right? So that's the interesting thing. Once you figure out something, you try all possible things, right? And she tried to find out if uranium is unique in producing the radiation, or is there some other element that can also do the same thing, that also produces Becquerel rays. And to her surprise, she found one more element, which is called thorium, named after the Norse god Thor, right? God of thunder. So it's named after that. So thorium was also emitting Becquerel rays, right? Very similar to uranium. And that is when she decided that it's not uranium rays or Becquerel rays, rather she coined the term radioactivity, right? And she called this phenomenon radioactivity. So it was not limited to uranium, right? There was other elements also. And then she would borrow ores from people who are mining all these, from the mines, and she would borrow them and she would investigate them. And sometimes she would even get from museums, right, the samples of the ores, and she would investigate for these Becquerel rays. Now, the minerals that contain uranium and thorium naturally would be radioactive, right? But what she found was the amount of radioactivity, the amount of radiation that should be coming out from these substances was not matching with the amount of uranium and thorium that's there in that material. Okay? Meaning you were getting more radiation than you should be getting. Now, what does that indicate? If you're getting more radiation than what's supposed to be coming out, that means you haven't taken into account everything that's causing that radiation to come out. Maybe there's more than uranium and thorium that is producing this radiation. Right? And it is only through careful investigations that you can find this out. And that's when she concluded that there should be something else in these samples, in these ores, which is much more radioactive than uranium or thorium. Okay, so which is causing this extra radiation to come out. And by the way, the processes through which she came to these conclusions, right? Those are grueling processes. Okay, first of all, there was no good laboratory. Basically, it was a horse shed that was converted into a laboratory where she was working at. Right, there was very poor hygiene. There were no advanced apparatus available. There were very primitive things with beakers and large vessels in which you could prepare solutions and so on, right? And you could heat things up. And it's a very physically demanding work. Okay, what she did, to the extent that her husband, who was not as strong as her, would rather do other things. He would help her out with other things, but the actual physical labor, Marie Curie did all of that, right? Being a very strong, physically strong as well. Right? And then she continued doing this, and she's basically dealing with radioactive material while not taking any precautions, right? What could be the reason for not taking precautions? Because today we know. Exactly, right? It's not carelessness, right? Rather, it is ignorance. You're trying to find out the very fact that it is dangerous. So you could not be careful while you're figuring out that it is dangerous, right? So eventually that had an impact on her health, and both she and her husband had very poor health throughout their life. They suffered from things that medical doctors could not explain, and that was because of the radiation, right? And now, based on her analysis, she concluded that these unknown substances had to be 300 times more radioactive than uranium. And then they set out to isolate this new substance, right? If there's this new thing which is, scattered in that ore, apart from uranium, why not filter that out? And then she took the help of her husband in grinding ores and trying to isolate one step at a time. And once they had enough concentration, then they declared that this is a new element, right? And naturally, she named it polonium after her motherland, right? Her birthplace, Poland. She named it after that, right? Polonium. This was the first element that was discovered based on radioactivity, right? Because it is radioactive, and this was what was causing that extra radiation to come out, right? This was a new element that was discovered. So you see, there are different ways of discovering new elements. All the elements you have in the periodic table, this is one of them, right? Through radioactivity. And so this timeline is wonderful. All of this happened in a span of 3 years, right? Starting with 1896, when Becquerel got interested in finding out whether X-rays are being produced by uranium. Then Marie Curie started investigating Becquerel rays, and she found out that it's to do not just uranium but also other substances. And by 1898, within 2 years of this investigation, they had already discovered a new element, polonium, which was producing radioactivity. Right? And so this was a serious event which happened, in fact, within, I think, 2 years, right? From 1897. It was in 1896 that Becquerel first started, February 1896, and by July of 1898 they had discovered a new element based on that. Right? So this was the triumph. In fact, they won the Nobel Prize eventually in 1903, all three of them. Right? Becquerel got half the share, and Pierre and Marie Curie got quarter and quarter. Right? And the sad part is, they wanted a laboratory more than a Nobel Prize. And unfortunately, the government at that time didn't recognize their work and did not approve them a laboratory. Right? And in fact, Pierre Curie got many more other, recognitions and awards, many of which he rejected, saying that don't give me awards and honors, I need a laboratory. Right? But he then neither got the laboratory nor the rewards, right? So unfortunately, and he died in a. Sorry, the cash prize. Of course, it came with cash prize, but that cash prize was not enough to, it was shared first of all among the three, and it was not enough to set up a good laboratory. Right? So you need more investment. And nobody, unfortunately, was willing to come forward and make the investment and give them a lab. It was only in the later years of Marie Curie, after her husband had died, he basically died in a horse cart accident. There was some horse cart that rammed across him and killed him. Whereas Marie Curie lived on much longer, but she got a good laboratory only much later in life. But all these, Nobel Prize worth discoveries were done in the most primitive laboratories. Like I said, it was a horse shed and under very poor conditions. So all the 36 years of her work, right, until her death, it was all obsession with the ores. Get the ores from the mines, purify them, and try to extract the stuff that is radioactive. Right? So it required great physical stamina, intelligence, and some stubbornness that I'm not going to let this go. I'll just until I have separated or filtered that particular substance. And you continue doing great work, you get great discoveries. They discovered one more element which they called radium, right? So those were the two things that the two elements that the couple gets the recognition for discovering two new elements, polonium and radium, which became part of the periodic table. Right? And basically what the ores that they were getting were all leftovers from, nobody cared about those ores. They extracted all the uranium, and whatever was waste they would be happy to give away to the Curies. But they knew the value of it because that contained radium. But from that they extracted radium from that waste, and that is how they discovered. And so it produces heat. Along with the radiation, there's some heat also being produced. So there's the question of, if law of conservation of energy is valid, where is all this energy coming from? And there are all kinds of speculations. Marie Curie gave one hypothesis that maybe there's some invisible radiation everywhere in the universe, and these radioactive materials seem to be the only ones that absorb that radiation, and they're giving out this radiation. Because at that time it was not properly understood. Because naturally the question arises, right? Where is this energy coming from? If this radiation is coming out, where is it coming from? With cathode rays you could explain. Cathode rays are basically beams of electrons coming out. X-rays could also be explained because it's electrons that come to a halt very rapidly. When they hit the glass, that's when the X-rays are produced. So there's a mechanism for them. But for Becquerel rays, for radioactivity, there seems to be no easy explanation, because it turns out today we know that the only way you can explain radioactivity is by assuming atoms, and how atoms, in fact nucleus, right? How the atomic nucleus behaves, which we will discuss more in the tomorrow's session, right? And you see, her son-in-law examined her notebooks and found that they were all contaminated with radioactivity, right? Radioactive substance, including her cookbooks, right? She used to cook at home, and the cookbooks were all contaminated with radioactive substance, right? And they continue to be radioactive even today. And so you can imagine the amount of radioactive substance that she would have ingested, right? And which ultimately caused her blood cancer, of which she died later. Right? This I'll tell you about later, okay, tomorrow. So anyway, so this was the series of discoveries that got us started with understanding the nucleus. Okay, so you see, we take a step back and we see all the series of events that led to the ultimate discovery of the nucleus. And later we'll see how other people took this forward. Marie Curie didn't investigate much further into it because she was more obsessed with getting radioactive substances, purifying them. There are other people like Rutherford and a number of other people who came up with ideas for how this is happening, what's happening exactly, what kind of radiation is coming out. If there is radiation, what is the nature of that radiation? What is the process through which the radiation is coming out? Right? All these investigations were done, and about which we'll discuss tomorrow. Okay. So if you have any doubts, any questions, any comments, feel free to speak up. So I hope this was useful, right? So and it was new, I hope, not something you studied in 9th and 10th grade, right? And so I feel this is important to know, because it's not just, I could have, in fact, thought about it for a moment when planning this course. Why not start with what a nucleus is, okay? And then I tell you it's protons and neutrons and so on, there's a strong force, but that would feel very aloof, because I'm just delivering you facts. Even though, of course, that helps you to understand the nucleus, but it's not very natural, not as natural as going through the history of it. So I have shown you how a series of events, one thing led to another, and ultimately we arrived at a situation where, you see, in fact, we have arrived at a situation where you cannot explain radioactivity, right? And that is where the nucleus comes in. It's only when you assume that there's not just an atom but a nucleus inside the atom that you can explain radioactivity. Right? So this is a very strong situation where it's a necessity. It's necessary to assume that there's something called nucleus and proceed. Otherwise, you are stuck there. Right? You cannot explain radioactivity using any other mechanism. And this was the birth of the idea of nucleus, which we'll see tomorrow, which happened with the very famous experiment of Rutherford. Right? Okay. Welcome. Welcome. Bye-bye. Welcome. Anyone can join. Yeah. You just have to tell me what the number is. I'll include them in the group. Or even if you would like to forward the link to someone else, also feel free at the Google Meet link. It will be a different link tomorrow.